Alright, the king is back. So we want to show that, I think this is what we have to show, that if G is, or we want to show that G is in Hamilton cycle if and only if f of G is in TSP. I'm pretty sure this is what we have to do, right? Okay, yeah. So obviously it's a two-way implication. We'll first show this way. Suppose G is in Hamilton cycle, then if there's a solution, Okay, let's think about this, because we're just adding a weight of 1, right? Then how would I say this? Then there is exist, then FG, then TSP has a solution, in f of G where K is the length of, or the number of vertices, right? Oh, she has it. Okay, I'm pretty stupid. What am I do? Okay, yeah, I'm kind of stupid. It should be, so if you want same sequence, yeah, power weight n. So okay, you know, yeah, that's true. Okay, so actually, if we suppose G has a Hamilton cycle, if we follow the same sequence in G prime, we will get a path of weight n solving the TSP. Right, so TSP solves to be true. And then the other way around is the other implication. Now suppose G prime can be solved with TSP. Oh. Right, I mean, I guess we say, okay, I guess we can't really mention that TSP anywhere because TSP on its own is a Hamilton cycle, right? So instead we say that there is a Hamiltonian cycle with total weight at most n. Okay, yeah, that makes sense. Suppose G prime has a Hamiltonian cycle of at most n. There cannot be any edges in with weight infinity. Thus all edges are present in G. And conclude G having a Hamiltonian cycle. Okay. Now, we want to define 4 sats and prove that 3 sats can be polynomial only time reduced by 4 sat. Oh, that's cool. Okay. Okay. So 20. Okay, so 4 sats. Obviously, if we remember, sat or any sort of sat is some, okay, maybe m clauses or n variables, sort of like that, except 4 sats. And then we have k sats. It should be k clauses and k variables, I'm pretty sure. Right? I'm pretty sure that's how it is. Just change 3 for 4. Consider Boolean formula phi with variables x1 to xn of the form phi equals to c1 conjugated to cm, where each ci is of the form. Okay, hold on. Let me ask Claude. When you have some case sets, does it have to be k clauses and k variables? What? What is this? That's weird. Timeout. Okay, let me just make a new one. Okay. What is going on? Am I getting trolled? Okay. I guess they're just trolling. Can I just ask someone else then? The k and k sign are related number of variables formula, or yeah, literals I meant in each clause. Okay. Okay, so the case that we can have, actually, I guess I was wrong. We can have m clauses, but k literals. So m clauses and k literals. This is what k sat means. Then for sat is the conjunctive of some clauses. For sat is conjunctive of clauses. C1 and CM, where CI is of the form L1 or L2 or L3 or L4, where any one of these is just a literal. What's the problem again? So this is the definition of for sat, and then yeah, so Boolean formula of the form phi equals to this, where you see as of the form like this, and each, what the, oh yeah, so we actually do need to add an I right here because there are for stuff, or for literals, and each, yeah, and then each literal ij is a variable or the negation of variable. A variable or the negation of a variable. And then want to show that this 3 sat can be probably reduced into 4 sats. Okay. Okay, so let's actually mention this. Then to show, if we wanted to show 3-sat is that could be polytime reduced by 4 sats, we need a function f where where f maps the input for 3 sats to an input for 4 sats. Wait, what? Then it should be... Okay, then then 5 prime. Okay, no, then we need some 5 prime. 5 prime in 3-sat and f of 5 prime equals to some phi. I think this should be it, because what? Okay, I guess this naming convention kind of sucks. Okay, this naming convention sucks balls, dude. Yeah, this input sucks balls. F maps and inputs for 3 sats to 5 prime equals f of y and inputs for 4 sats. Okay, and then so we need to satisfy this. We also need to satisfy if phi is in 3 sats, or not if, we say that phi is in 3 sats if and only if 5 prime is in 4 sat, or in other words, f of phi is in 4 sats, as well as f of phi can be computed in polynomial time. Okay, now this is sort of kind of weird part, because we know that for a clause in 3-sat, a clause ci in 3-sat is in the form L1 or L2 or L3, but any clause in 4 sats requires for literals. Then we can probably do something where L4 equals to L3 or L3, because any L or any literal is equivalent as the disjunction of their self, right? We can sort of look at this, right? If we have L and L, or L, if we have true or false, if this is true and this results to false, so we know that this is true. So I'm not sure if this is what they're expecting. Okay, yeah. So this is what they're looking for. Okay, yeah. So we define find C prime I equals L1 or L2 or L3 or L3. Now obviously if phi is a valid input. Wait, how? That's a weird way. Okay, so we can say property 1 so property 1 is can be verified since any valid phi in 3-sat phi prime is a valid input for sats because each clause C prime I in 4-sat is composed of 4 literals posed by the disjunction of 4 literals. And then property 3 is also verified since we just have to scan all the clauses in phi. You scan all the clauses in phi to build phi prime, which is O of m to the 1 time. Now we want to prove that. Lastly, we want to show any phi in 3-sat if and only if phi prime is in 4-sats. So we first show, so it's a double implication, so we'll show this first. Let me show this. Phi is satisfied. The proof of property 2 is based on the observation that any literal equals to the disjunction of themselves for all literals L. Okay. Okay, I think this is like a pretty neat trick that it's pretty hard to notice. Oh my god, there's really so many problems here. I didn't even realize. There's actually so many problems here. Okay, I think this is a very neat solution where we note the fact that any literal L is equivalent to disjunction of themselves. So phi is satisfiable. Then it means there's a truth value assignment such that there is a truth value assignment such that phi is true, equivalent to and then this is equivalent to for all one, or is for all i's, ci equals to L 1 Li1. Actually, I guess I don't have to mention that. Okay, never mind, I do have to mention that. For Li2 or Li3 evaluates to true. So Ci evaluates to true, and this is equivalent to for all is more than I is more than M, Ci equals to L, or C prime I equals to Li1 or Li2 or Li3 or Li3. Ci evaluates to true, and it's equivalent as phi prime is satisfiable in 4 sets. I feel like it's such a stupid thing. Satisfiable. Okay, I think this is a pretty neat question. Oh my gosh. Okay, I think I'm gonna take a little break from this unit. You can do some exercises for 1, 2, and 3 probably. Exercises, solutions, exercise, solution, and then let's look at the notes. What is chapter 1? Okay, actually, let me just look at the course's outline again. Let me look at the units. I don't know how important this is. Introduction, divide and conquer, graph, greedy, DP. Yeah, like these ones are pretty easy because I knew them pretty well. I don't know how important lower bound arguments are. Because I don't think there was problem set for this. Was there? There's no chapter 7, so it's not important. Okay. This chapter 1. Okay, wait, this actually. Okay, I won't do this bit because it's kind of stupid. Because I'm not writing down no pseudocode for insertion sort. Like, I think this is just plain stupid. I think I'll start with number 3. And then I could do number 4. That's fine. I think this is cool to do. I'm not gonna do this. Okay, yeah, let's do chapter 1. Let's do chapter 1. And chapter 1, we can begin with question 3, because I'm not doing those two. We can begin with question 3. And then let's update this a little. So instead of P equals to NP, it should be basics. It will be basics for now. Okay. So I think I'll minimize this because it's actually pretty doable from my screen this way. Actually, should I download this somehow? No, that's pretty dumb. Okay, number 3. What are the common operations we perform on the following data structures? Oh. Next. Okay, that's weird. I think this is next, and then B is next, and then before was previous, and then min heap, push pop, the BST, bounds BST. I mean, you can really just go left to right. Left to right. One dimensional array. Like, we have operations. I mean, we can insert, we can pop. And then two. Okay, actually, I don't even, like, what's the answer for this? What's number 3? Oh. Okay. That's pretty dumb. Okay, 4. 8. How much time does it take to perform each of the following tasks? Such as insert, blah, blah, blah. Search for elements in singly linked list. This is O of n. B, doubly linked list, also O of n. Sort of singly linked list, also O of n. Sorted doubly linked list. That's also O of n. Because you can't really, like, find it by index, you know what I'm saying? This is also O of n. F, maximum elements in a doubly linked list, O of n. Holy shit, everything is O of n. That is definitely O of n. Okay, I'm not quite sure about H, because I don't know if you are given, like, I don't know if you're actually given the pointer or the node of this W like list. But sure, I'll say it's O of n. Search of an element in an array, O of n. Search for an element in a sorted array, that's log n. Of log n. Okay, find the minimum element in a one-dimensional array, that's O of n. Minimum element in a sorted one-dimensional array is O of 1, O of 1. And then M, find the minimum element in a two-dimensional array, that's O of n squared. Let's check this. Okay, yeah, O of n. Okay, yeah, so for H is actually O of 1, so you are given the pointer. That was the only thing that I wanted to know. So everything is O n up to O8. H is O of 1, and then I is O of n. Log n, O n, O1, m times n. Yeah, sure. The n squared, but it's like the same thing, whatever. No, I'm not doing. Actually, am I doing this? Okay, yeah, I'm doing number 5. I'm gonna do number 5. Number 5. A, true. B, true. C, n divided by log n. I mean, that's like the same thing of multiplying by 1 over log n, which is n log n question mark. So I think this is false. And then D, I'm gonna say this is false too. D is false. E, that's most definitely false. F, false. Actually, could be true. F could be true. G is... Okay, which one's bigger, log n or root n? I'm pretty sure log n is bigger, so this would be false. H, n times root n. And then what was the conclusion we drew earlier? Log n is bigger than root n. In that case, this is true. I, that's true. J, true. K is not true. Actually, no, I think K is true. Actually, no, K is not true. L, that is most definitely not true. Okay, let's see. True. Okay, this is false. Why is that? There's no constancy such that 1 is smaller than C times 0 for larger n. Oh, there was an O of 0? Okay, I didn't even see, so this should be false actually. And then... oh, this is also true. Okay. Oh, right, because n divided by log n is smaller than O of n. So yes, that's true. And then... this is false. Yep, this is false. Yep. This is false. This limit is infinity. Oh. Okay, I forgot the math level, so it's false. And in any case, which is bigger? Is root n bigger than log n? Okay, root n. Okay, if root n is bigger, then this should be true because root n is bigger. And then in this case, this is false because root n is bigger. And then this is true because base 3 is bigger, or even that too. Then this is true, false, false. Okay, that's cool. And then this is just asking for the running time. Okay. We say that root n is bigger than log n. So we're not doing 6, we're doing 7. So an algorithm finds the largest number in the array of n numbers and analyzes run times in the worst case. So keep a local max starting at 0. Okay, actually no, not starting at 0. Starting at array at 0. And scan through array at 1 to n. Update local max if a at I is greater than, actually no, keep a result variable, so greater than update results if AI is greater than results of n time. Okay, so this is A, and then there should be a B. M smallest integers in the array n, and analyze the running time of worst case. Okay, I mean, sort and return return A at 0 to 2. Of n log n, and then I can you do it in of n time if m equals to n minus 3? What? So if n is 7, then m equals to 4. I'm not sure. Okay, let's say you have some super big number. Okay, yeah, you can. I'm pretty sure you can. Well, actually, can you? Yeah, you can. You definitely can. I think you can. What's this? The hell? What the hell? Wait, why can you not sort this? What the fuck? That's pretty stupid. And it's gonna ask for brute force. Okay, I think these questions are getting pretty stupid. Wait, let me do the runtime questions. 11. What is the running time of the following algorithm? Input, the number n is even. So 1 to 3 over 2n, you print I. Okay, this is of n. It's pretty stupid easy. 12. What is the running time of this following algorithm? J equals to 1 while j is smaller than 1/2 n to I equals to 1, and while I smaller than j to I plus plus. Okay. I feel like it should be n log n. I feel like it should be n log n. Either that's or n squared, but I'm leaning towards n log n because it is multiplied by 1/2. 13. Let's run over this algorithm. 2 to n. Okay, yeah. Okay, now this part is n squared. I'm pretty sure this is n squared. And then 14. Run over this algorithm. 1 to n. J greater than 1, do this. That's n log n. That's O of n log n. And then let's run over this algorithm. I 1, do j equals 1, j 2 times j. I feel like this is n log n. This is most definitely n log n. It's definitely not n, because I think times 2 and divided by 2 is very different. So this would be an O of n log n. 16. 2 times I plus 2 O of n. Anytime you have something with multiply, it's just always O of n. I don't know why that is. I don't really care, but that's it. Number n is an integer. Okay, that's log n. 18. What's the running time for this algorithm? Okay, so this is O of roots n. I'm pretty sure this is just what it is. Let me see. O of n squared. Okay, this n squared. And this is n. Okay, that's not good. This is n squared. I guess I should just look next time because it's pretty dumb. N squared. This is n. 14 is n log n. 15 is. Okay, this is just log n. What? I guess this is also log n. Wow, I suck at this. Holy crap. Oh, oops. What the hell? This is some weird ass shit, dude. Well, I'm getting kind of cooked. Now, let me work on past midterms. Okay, so I can work on. Yeah, I can work on these two. That's okay. Midterms. I don't think these problems are too hard. Should I download this? I'll download this. Gotta send it to myself. Can't dox myself. Okay, I'm just gonna open the whole thing on my iPad. Oh, that's not good. Okay, let's work on this. Using n as input size, what is running over each algorithm? So product was a 0. That's one product. Okay, I don't know if 2 times I count as log n. Let me ask. Does 2 times I equals log n? Okay, I'm gonna say that it doesn't. It's gonna get out of the screen. Okay. Okay, so this doesn't matter. Doesn't matter. This is. Does this count as log n? I don't think so. So I think this is just O of n. I think it's O of n. What is the running time of the following? Okay. I feel like this is n log n, I think. Or it could be this. It's either n log n or log squared n. Oh, this shit. I think this was, what's his face? Master's theorem. I think this is a master theorem. Something like that. Let me read this again. So if you can okay, yeah, here it is. If you can divide it into this subproblem, then so for subproblems n divided by 3 takes O of n time. Okay, I'm pretty sure it's this. It has to be this. It's always this. That's what the whole master theorem's about. Okay, yeah. Master theorem. And if G is a tree, how much time is Dijkstra's on G? Weighted directed graph and adjacency list. Okay. Okay, I feel like it's n log n or n squared log n. It's one of these two. Dijkstra's algorithm repeats the source. What order do the vertices include in sets? Okay, the way Dijkstra's work is... Oh, yeah, it's a single source algorithm. Yeah, okay, so P is a source. Okay, so you start from P, so 1, and then you take the smallest one, which is the next one, which is 1, so it's the Q. Take the next smallest one. Okay, we also have to accumulate this, so currently is 1 plus 1. This is 2, this is 3, and then 3, and then this is 4, then 4, and then this is 5. Now 3 plus 2 is 5. I already visit this, so it doesn't really matter. 6, 8. I'm pretty sure this is the order. So P, Q, R, U, S, T. P, Q, R, U, S, T. It should be this one. Oh, what the hell? Wait, what? Oh. Consider the follow direct graph in G. Oh my god, I actually forgot so much. So we run a depth first search on G starting at A, write the pre-numbers and post-numbers. Okay, so we start from A, so the pre-number is 1, and then we go to B, so the pre-number is 2, then we go to C pre-numbers, C is 3, and then 1, 2, 3, and there's nowhere else to go, so post number is 4, 5, 6, and then A, B, C, D, so 5, or not 5, 7, 8, 7, 8, 9, 10, 11, 12, this should be it. Okay, use selection. Is it? Okay, so obviously some things that you can do. You want to be popular, so we can use something called quick select. Quick select or sort and count. If we sort and count, this would be n log n. Now quick select, I'm not very sure. Okay, quick select is O of n, but how do you make sure that quick select is the 1? I kind of forgot how quick select works, so I might have to revisit that, but I'm pretty sure that should be the answer. Some infograph G is stored using the adjacency list. We assume that vertices is 1 to n. We not assume that adjacency lists are specified in any specific order. Now, an undirected graph G together with 2 vertices A, B, and V. List of all vertices V, such that V is adjacent to both A and B. I mean, we visit all vertices. Okay, then, like, I don't know how much better you can do this, just DFS, like how much better can you get? Oh, it tells me here, okay. It gives you the master theorem. Okay, yeah, I can't think of anything else. You just run DFS, or not DFS, sorry. You scan the adjacency list at every vertex except for A and B. And brute force check if both A and B is in the list. So if we have n vertices, we can have at most n-1 connections. Then it's just n squared. So there's just O of n squared. Or no, actually no. No, you can do something else. Scan adjacency list at both A and B if they're edges, or if there are nodes that are in both lists. Return those nodes. So this is actually O of n. N times 2. Let's read. Let's compare our solutions. Okay, so this login. Okay, I knew it. I feel like it had to be odd n. Okay. In this case, exactly login. I always forget my asymptotic shit, bro. And then it was either one of these two. Wait, what? This is number 2. Am I on the right one? Okay, no, I'm definitely on the right one. Oh, 2 is O of n. Oh, 2 is O of n? Why is this O of n? That's pretty dumb. Number 3 is this, which is I'm right. Number 4 is n log n. Yup, n log n. So it's this one. Number 5 is PQ Rust. Yup. Then let's look at this. 1625340 7, 8, 9, 12, 10, 11. That's fine. Okay, so I guess you quick select 4 times. Okay, unlock N is worth 6 out of 10. That doesn't compute 2 times N. What the heck? M1 occurs more than N times 3. Okay, you know, this is like a neat solution, I would call it. But yeah, you use like quick select here. Yep, oh, event you check both adjacency list at A and B, so that's true. Okay, that's done. Wow, I kinda stink. What the heck?